Here we are on the week number 11, stiffness method for trusses, right? So we're going to discuss the stiffness method for trusses. Now, revision of the moment of distribution. Last week we talked about the moment of distributions. There are few terminology that I have introduced. You can find the stiffness of the beam elements. So that is the stiffness of the beam elements. When your far end is fixed, you can use this 4 EI over L. When your far end is pin or rollers, you can use 3 EI over L. So there are two only equations to calculate the stiffness of the beam elements by looking at the far end of the supports, like the fixed supports and the pin supports. Now, after that, we also discuss the distribution factors. That is the stiffness of the each element divided by the total stiffness of that particular joints. If you look at the last week lectures recording and the workshop examples, you will find the information about the distribution factors. We also discussed the carryover. That is the half of that moment that you are carry over. If you have a overhang beams elements, then you can just convert this one into the respective concentric moment, and you can ignore this particular part of these values. Now, in here today's, we are, as you know, for 6 weeks, it's about determinant structures, and we have successfully finished those for 6 weeks. Based on that, for 6 weeks, we have submitted the assignment, and our quiz also finished. After the semester break, we have started the energy methods. There is a questions 1 from these energy methods for your assignment number 3. There is a second question from the force methods in your assignment 3. There is a question number 3 from the slope deflection methods in your assignment 3, and there is a question number 4 for the moment distribution methods in your assignments. And final questions for your assignment is coming from this week, which is the question number 5. Some students requested the extension for the assignments because there may be other assignments due on this particular week. So we have given you some extensions, probably 1 week to submit the assignments. So you can check the new date on the assignments. Here now. Thank you who already filled it out. Now, this week's we're going to work on the lectures that's going to introduce the stiffness methods. Very powerful methods, by the way. That stiffness methods that we're going to discuss today is a very powerful methods. And it will be used to analyze the truss. It can be used to analyze the beam. It can be used to analyze the frame. So it has everything, right? We are not going to teach you these ones. We are not going to teach you beam and frame. If you want to learn, you need to join our master course, Master of Engineering. I'm taking the one subject in Master of Engineering where I'm teaching beams and frames. But for these subjects, we are just drop at trusses. The stiffness method can be applied for both determinant and indeterminate structures. Very powerful. It can be used for determinant structures and it can be used for indeterminate structures. It can be used for trusses. It can be used for frame. It can be used for determinant structures, indeterminate structures. You name it, these methods will do it. Right? Very powerful. Latest methods that you are seeing it here. The space gauge software that you are currently using it for your assignment in last 11 weeks or last 10 weeks. The stiffness methods, the space gauge softwares are built on these stiffness methods. So behind the screen, the stiffness, the space gauge is using the stiffness method. So today we are teaching you, I'm teaching you the methods that the space gauge softwares use to solve the analysis problems. In the futures, if you are powerful, you can develop the softwares like the space gauge because you already know the stiffness methods, and these stiffness methods basically give you those kind of tools. Yeah, so introductions. You remember that we started with the force methods. If you remember that we started, let me go back all the way here. That we started with the force methods. We started with the force methods, right? Energy methods and force methods. That is the determinant structures that we started here. Now, in the force methods, your determinant static degree of independence D equal to 1. If you have static degree more than 1, then these methods is kind of a challenging. If you remember that, right? You need to go for a long way. Then the slope deflection methods comes and they said, oh, degree of determinacy 1 or degree of determinacy 2 is gonna work. But if it is more than 2 or 3, it will not gonna work. You can see that. Then we come here, then say that, okay, any degree of indeterminacy is gonna work. But these methods does not apply to the truss. It just works with the beam and frame. These methods only apply for the beam, right, and frame. These methods again. So every method that you have seen has a disadvantage. They have some kind of, they can be degree of indeterminacy 1, they can be apply only beam and frame, cannot be applied for truss. There are long methods, very challenging, very problematic methods that we have. Even we can't use these methods to develop the software. The space gas cannot use these methods, that 8, 9, and 10. These stiffness methods, very powerful methods. It can be worked for any degree of indeterminacy. If you use a very highly undeterminate structures, D equal to 1, 2, 3, 4, 5, 6, no problem for stiffness methods. If it is beam, no problem for the stiffness methods. If it is truss, no problem for stiffness methods. If it is frame, no problem for truss methods. So you name it, the stiffness methods do it for you. And therefore, it is a powerful method. Then someone said, what about the computer softwares? Can we build the computer softwares? Yes, stiffness methods can be used to build computer software. So this is a very advanced methods. We still use it in our analysis. And that's here we are teaching you these methods. Now, to teach these methods, I need to provide you some vocabulary. There are about 400 softwares around the world that are used by the structural analysis. Even now, 500 maybe. All these softwares are based on these stiffness methods. The fundamental theory behind all these softwares like Abacus, SpaceGas, ANSYS, there are few names that I provided, highlighted here. These are the finite element softwares. Finite element softwares that you are seeing here, they all use the stiffness methods. Now, what is finite element? Let me brief you, explain you. So the finite element softwares meaning that, let's say if I give you the square, and let's say the A and B is the width and height of the square. If someone asks you to calculate the area of the square, you can say these dimensions times these dimensions, I can find the area. For example, let's say this is 5 centimeters and this one is 5 centimeters. You can say that the area equal to 5 centimeters times by 5 centimeters. I can get 25 centimeters square. Easy peasy, no problem. Now, but if I give you the problems, which is like this. If I give you the problems, which is like this. Can you calculate the area for this one? Like you calculate the area, which is 25 centimeters square. What would be the area here? Let's say I give you these dimensions again. Let's say this dimension is 7 centimeters and this dimension is 5 centimeters. Let's say I give you these dimensions too. Are you able to calculate the area, cross sections area of these ones? Yes or no? Like the one on the left side, that's I'm rolling it. Probably the answer is no, you can't calculate this one using our standard formula, right? The one that I shown on the right side, right? So yeah, but not conveniently. Yes, you can calculate, but not conveniently. It is inconvenient to calculate these ones, right? You can do various things, but not straightforward like this one. But what if I tell you we can do this? What if I can tell you that, how about we know the area of the squares? So how about we just divided them into the small, very small grid like this, very small grid and same grid, okay, like very small grid. And if I know the area of this one grid, like area of one, and if I calculate how many square in that one, so let's say I have 1000 square here and each square has a 2, then I can say that the area would be, let's say, 2000, right? So that is the finite element method. What's the finite element methods do? It takes your complex structures and divide it into the very small groups. Someone will come back and say that, hey, Vipuls, what about this area which is on the corner? Because it would not be the square, it would be like a kind of a triangle with the curved line. Yes, I agree with you. So this is the approximate methods. The smaller the grid that you're going to make it, the closer the area that you're going to find. Yeah, so this is an approximate method, but it still works in the structure analysis. It still works because we are not looking for exact answers. We might have a minor error that can be acceptable. So our structures will not going to fall down. No one's going to fall down with that minor error because we have factor of safety. Still it works. Still it gives you the answer. It's still behaving within our range. So still works, no problem. So that tiny portions of that outside zone, like the one here, let's say the one that is here, like this one. So that's pretty much not give you the right answer, but that's okay. We can give you the closest answer. So that is the finite element methods. What the finite element methods do, it will take the geometry or materials and break it down into very, very small segments. And then it solve that one small segment, and then it will add up. So I hope it is made sense. You take the one small element that you already know, the area or something, and then you add it up all these integrations. Then it will give you the final answers. Does it make sense? Like the overall theory. Does it click? What is the basic, the fundamentals behind it? Yeah. So it is. I'm not asking you to going to define the stiffness methods in the final exam, but I hope it is kind of overall nutshell. So now that's you understand. So let's say someone asks you to solve these problems, which is on the left side, right? Someone say that, can you please find the reaction force? Can you please find the internal forces? Can you please find the displacements? Someone tell you to do this ones. So by looking at the left side, it looks very complex problems. As I said, these examples which I give it to you, it has a very complex pattern. What if I divide these ones into the small grids and then take each grid, take this grid and work on that one because it's a square, and the engineers like this square because we know the area, we know this, we can do many things on the square, but those kind of geometry is not a problem. So what we do the modeling. So this is called modeling. This process that I divided, that is called modeling. So we do the modeling on here. Now let's do the modelings on here. Please focus on 5 minutes with me and put everything on side. If you have phone or checking on the Facebooks or something, just keep it on the side. Very important right now. That will be useful for the further. If you don't understand this one, it will be difficult for me to go ahead and explain you further. So on this one's on the left side. This one on the left side, you have how many members? 1, 2, 3, 4, and 5 members. So you have 5 members. So let's say we give them name 5. So number 1 with the square is representing the member numbers. Member 2, member 3, member 4, and member 5. Do you understand, everyone? What I've done, I take the whole truss systems and I divide it and count them into the 5 members. So 1, 2, 3, 4, and 5. The number with the square represent the member numbers. Now, it is matters if I put the 1 here and 3 here and 2 here. It does not matter. It is a user defined. Your answer will not be changed. So if you put 1 or if you put 2 or 3, this is a user defined arbitrarily. There is no any specific or engineering rules which one goes 1, which one goes 2, and which one goes 5. There is no any rules for this kind of a modeling. But that is the very important. But once you define it throughout the process, you can't change it. Once you say that this is my number 1, this is my number 2, this is my number 3, this is my number 4, this is number 5, stick to that one. You can't change your mind in the middle of the example, say that, okay, I want to make this one more. No, not allowed. Once you fix it, you no need to change it. Right? So that is the theory. 1, 2, 3, 4, 5, arbitrarily, no rules. You don't need to worry about which one goes first, which one goes later, and which one goes after. Does it make sense? Does it make sense? 1, 2, 3, 4, 5, all good. Yeah. So 1 students, yep, all good. So that is so far so good. So that's number done. Now, arrow is called location vector. This arrow is called location vectors. What is the importance of this arrow? The importance of this arrow is called, okay, before we put on the arrow, before we put on the arrow, let's put these ones. Number 1, number 2, number 3, and number 4. Now, number with the round that represent a node number. Number with the round representing the node numbering. So that is the node number 1, like you can say joint. But in the stiffness method, the vocabulary that we use is a node. So node number 1, node number 2, node number 3, node number 4. Again, there is no rules which one goes number 1. You can put number 1 here, you can put number 2 here, you can put number 3 here, you can put number 4 here. There is no rules that 1 with the 1 should goes here. No, there is no any rules. You can change whatever you like it. But once you put it this one, you are not allowed to change those numbering throughout your example until you get the answers. Right? And again, there are 4 nodes. How do you recognize? Because there are 2 ones. So one with the square brackets represent the member numbers. One with the circles represent the node numbering. Now that is a location vectors. That location vectors are sitting here. In that location vectors, you can say that this is a near node. This is a near node. This is a far node. Right? Near, far. The tail of the arrow represent a near node. Head of the arrow represent the far node. If I put the arrow here, then for member 4, this is a near node. This is a far node because the tail of these members of these location vectors representing these ones. Now, if I put the arrow here, can anyone tell me for the member number 5, which one is the near node and which one is the far nodes? The node number is 3 and 4. Which one is near node and which one is far node? For member number 5, location vectors are representing in these directions. Which one is the near node? 3 is the near node, 4 is the far node. Thank you. That is correct. 3 is the near node, far nodes. Yep. That is correct. 3 near, 4 far. That is correct. Now, if I put the arrow going in these ones, for member number 3, there are 2 nodes, which is the node number 3 and node number 1. Which one is near node and which one is far node for member number 3? If I put the location vector here, yep, 3 is near, correct, and 1 is far node. That is correct. Again, location vectors does not matter. Location vectors does not matter. You can put arrow the way you're gonna like it. Does not matter. Your answer will not be changed. But the rules is you must have those arrows in place when you do it. Now, the last one that I like to explain you, that is this numbering. So these numbering, which are going to put the green one, 3 and 4, 7 and 8, and 1 and 2, and 5 and 6. Right? So these are called degree of freedoms. What does it mean, degree of freedom? So this particular point here, I'm talking about very tiny particular point at the node. This node has a possibility to go in the C1. It has a possibility to go in the Y. So it can have a translation, it can have rotations. Now this point cannot go this way, by the way. This point cannot go this way, it cannot go this way, it cannot go diagonally. Because there is a truss system, so this point only can go this way or it can go up. Right? That is the green one. So that is the degree of freedom. Degree of freedom meaning the possibility of that particular point has a possibility to, when you apply the load, it can go either in the C1 or it can go in the Y. It cannot go diagonal. Right? That is a truss system. Similarly, this particular point has a possibility to go in the 3 and it has a possibility to go in the 4. So for this truss system, total degree of freedom is 8. Why? Because there are 4 nodes and each node has a 2 degree of freedom. So total degree of freedom is 8. The numbering is important here, which I'm going to explain you in the next few minutes. But do you understand all these ones? There are 3-4 things I explain you. You don't need to remember. And in the exams or in your assignments, we are going to give you these ones. in your exams, in your assignment questions, whatever you're going to look at, we're not going to ask you to model it. We're not going to ask you to model it, but you need to understand what those numbers, what those arrow represents, what those things are represent. That is your call. We will give you these informations, but you need to extract that information by yourself. So I think we discussed the node, we discussed the element. Element meaning this is the element. Element, that is the member, is the elements. Now, degree of freedoms. I already mentioned the degree of freedoms, and I'm going to further provide the informations about the unconstrained degree of freedoms and constrained degree of freedoms, or free degree of freedoms or fixed degree of freedoms. Please pay attention here that I'm going to explain you. Now, as I already mentioned you, how many total degree of freedoms here in these problems? Total degree of freedoms. Total degree of freedoms, how many here? In the last slides, I explained you that. How many total degree of freedoms? In here, total 8 degree of freedoms. I agree with you. Total 8 degree of freedoms. There are 4 nodes, and each node has a 2 degree of freedom. So total 8 degree of freedoms. Now pay attention here. Now pay attention meaning that there. Okay. So there are total 8 degree of freedom. Pay attention here. Now these. Let's start with node number 1. This joint. This particular point at 1, and it has a pin joint. It is a pin joint. It is a pin joint. So if it is a pin joint, this point, this tiny point cannot go in the C1 and that cannot go in the Y. You agree with me? Because this particular pin is holding that point so tight that this point, the support of the pin cannot go in here. That's the function of the pin, that this point cannot go here or cannot go here. So everyone okay. So I can say that C1 and 8 is a fixed degree of freedom because it is fixed. It cannot go. Fixed degree of freedom. You are with me so far? That is the C1 and 8 fixed degree of freedoms. Now this point here at number 2, that has a 2 degree of freedoms, one in the 3 and one in the 4. So 3 and 4 is a free degree of freedoms. You with me? Because there is no any supports on that ones. There is no any supports at point number 2. So this point can go freely at 3 horizontally, and it can go up at 2. So that's 3 and 4 is a free degree of freedoms. At number 3, 1 and 2 also free degree of freedoms. That is also one group here that is a free degree of freedoms. At the rollers here, this point cannot go in the X directions, which is at the 6, because these rollers will prevent to go these points going in this direction. So number 6 is a fixed degree of freedoms. Number 6 is a fixed degree of freedoms, but number 5, they can point 4 can go up and down in the 5. So 5 is a free degree of freedoms. Right. So we have total 8 degree of freedoms. Out of 8, total 3 are fixed degree of freedoms, and total 5 is free degree of freedoms. Do you understand that? I have total 8 degree of freedoms. Everyone told me that they understand that. And after 8, we have divided further to classify fixed and free degree of freedoms. We just take apart, add up to the 8, 5 plus 3, 8, but 5 are free degree of freedoms. The point which are not supported, they are free degree of freedoms, and point they are supported as a fixed degree of freedoms. Now that is all good. Now the rules is simple, that all your free degree of freedoms, and everyone understand that the total 5 free degree of freedoms. There are total 5 free degree of freedoms. Total 5 free degree of freedoms. So all your numbering to start with the free. So any ones that are free, let me show you which one is a free. So I can list them here. So this one is free. This one is free. This one is free. This one is free. And this one is free. And the red one, this one is a fix. This one is fixed, and this one is fixed. Now, that's all listed. Now, all your free degree of freedoms, that's we need to start with, because you remember that there are numbering. 1, 2, 3, 4, 5, 6, 7, and 8. There are 8 degrees of freedoms. We need to number them. So the lowest number, which is 1, 2, that will goes with the free degree of freedom. So you can put 1 degree of freedom here, 2 here, 3 here, 4 here, and 5 here. So lowest numbers, that always goes with the free degree of freedom. And I will tell you later when I take an examples why we do that once. And the remaining one that will goes with the fix. Let's say 6, 7, and 8. So that is no matters. You can put 1 or you can put 3, 4 or 1, 2 or this one, but within 5, you can distribute whatever you like. 1, 2, 3, 4, 5, whatever you like. But the first 5, which is we divided, that will goes with the free 1, 2, 3, 4, 5. So if you have to decide 1, 2, 3, the lowest degree of freedom numbering, that's always start with the free degree of freedoms. And the fixed degree of freedoms, that's the highest degree of freedoms. Now let's check your knowledge. Let's check your knowledge, whether you understand or not on these ones, on this concept, that one. Notice, by the way, you can ask me questions if you don't understand. How many total degree of freedom for this member here? How many total degree of freedoms? How many total degree of freedoms? How many total degree of freedoms for these figures? Anyone? If you understand these ones, how many total degree of freedoms? 10? Yep. Anyone? Someone say 8, 10, 10, 10. No one said 8, 10. Yep. I think majority is 10. So let me put this one. So you have 2 here, 4, 6, 7, 8, and 10. There are total 5 nodes, and each node has a 2. So 10 is correct. Node 8 was the something else. So sorry. Yep. So you know the 10. So everyone with me, there are 10 degree of freedoms. Now out of 10, how many free and how many fixed? You don't need to tell me which, but you can tell me how many free degree of freedoms. If you add up these ones, it should be 10. But how many free and how many fixed here? How many fixed degree of freedoms? How many free degree of freedoms? Four free, 6 fixed. 4 free. Yep, she said 4 free and 6 free. Yep. So let's put the green one is a free one. So you say that this one is a free. This one is free. This one is free. This one is free. How about these ones? This one free. Because there is a pin. This is pin. This is pin. And this is roller. So I would say that there are 5 free degree of freedoms. You with me? Or kind of? Yep. So there are 5 and remaining 5 is a fix, which is purple one is a fix. And that is a fix because roller can't go this way. Anyone? Yep, got it. Any questions? Any suggestion on that ones? Yep, all got it. Okay. Now my problem is I have 2 options. You can have a 1, 2, 3, 4, and 5. I have this numbering, or I can have this 1, 2, 3, 4, and 5. Now I need to give this 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5 allocated to someone because there are 5. Because there are 5 here, 5 here. Now the first 5, where does it go? Is it goes with the green, or does it goes with the free, or first 5 goes with the fixed? Based on the information which I have provided, which one the number is going to start? Which is going to start with free or it's going to start with fixed? Yeah, so it's going to start with free. So it does not matter which one going to start. We can start with 1, 2, 3, 4, and there's 5. And the remaining one that we're going to put is this one is a 6, 7, 8, and 9, and that's it, right? So that's the numbering that you have. All right. So I hope you understand all these ones. So so far you know how to do the modeling. You know the member number, you know the location vectors, you know the near node, far node, you know how to find the total degree of freedoms, you know how to do the free degree of freedoms, you know how to do the fixed degree of freedoms, you know how to do 1, 2, 3, 4, 5, and so on. Right? So all these informations which I have given you, that will be given to you in the final exams, and it will be given to you in the assignment questions. And the modeling, you don't need to worry about it, but you need to identify fixed and free degree of freedoms, and you need to know what those arrows and numbers are representing. Now, next one, when you take the trust systems, you have two kind of a system. One is a global system, another one is a local systems. Now, what is the global systems? The global systems representing, saying that when you have axes, that the coordinate systems that you're going to put it, that has a one axis, like X and Y. You can represent anywhere, like let's say this is 0, 0. And from this 0, 0, you're going to measure all these points. For example, let's say this is 1.5 meters here. Then you can have 1.5 going here, and let's say 1.5 up. So 1.5. Then you have a, let's say this is 3, 0. Let's say this one 3, 1.5. So based on this 0, 0 here, you will have a coordinate. You have a position of the each nodes and dimension and everything. That is the global coordinate systems. Now that global coordinate systems are used to define the external loads and displacement at the nodes. Right? That's the usefulness of these ones. Right? So I will explain you when we take an examples for the global coordinate systems. But keep in mind at the moment for the information that the global coordinate systems is something that is affecting all the nodes, and that is the reference point for whole systems. Reference point meaning you need to measure somewhere. Let's say 0, 0, 0. Right? So there is no rules. Which one would be the 0, 0? You can say that this is 0, 0. You can say that is 0, 0. No problem. Someone said this is my 0, 0. No problem. But once you decide that 0, 0, you're not allowed to change throughout the examples when you solve it. Again, we are giving you that 0, 0 to you. Reference point we will give you in your assignment questions in the final exam questions. So you don't need to worry about it, but you need to understand that that is a 0, 0 that you can take it, and this one. And that is a global coordinate system. It's help you to where the coordinates, where the loads, and so on, where at what point the loads are based on that 0, 0 reference. It is just basically where's my 0, 0 point for the whole system. So that is a global coordinate system. Now in the local coordinate systems, each member has its own system. So for example, this has 0, 0 here. That is 0, 0 for this member number 3. And then you have this local. So global coordinate system represented by XY, but the local coordinate system represented by X prime and Y prime. So every member has its own local systems. Let's say this is X dash, Y dash. Let's say this is X dash, Y dash. That is a local system, and these local systems are used to calculate the internal forces that represent the internal forces. Right? So don't worry if you don't understand. That is not part of the examples, but it's just kind of an information that I like to give you. Global systems is basically representing your XY whole systems. Local systems meaning it has member related system. So you can see that for particular member here, they have X dash. This is X dash and this is Y dash, and it has a local systems. Okay, so nothing too much worry, just the information that I like to give you here. Now, in here, don't worry if you don't get this one. So it's a little bit tricky, but I will try to make you understand these ones. Let's take a one road. Let's take a one members and let's fix it. Let's take a one member. Let's take a one road and let's fix it one end. And another end, let's pull it by the force Qn. N meaning near nodes, right? That is a near node. So when I push it, it will be deformed by Dn. it will be deformed by dn. So when I have hold it these ones, let's say if I hold it these ones and if I push this one, and that will going to deform by dn. Now, someone said that how much force you are applying, and you want to calculate that how much force you are applying. You can have very small equations. And by the way, if you don't understand, don't worry. Okay, I will just, this is little bit of materials and so on, but I'm going to show you how to do it. So if you know the stress is equal to force over area. And if you know, this is axial stress, by the way, axial stress meaning it is just axially, no bending stress. So axial stress and truss are axial stresses. And if I want to know the axial strain equal to change in length over original length. So how much it's deformed divided by original length. And the Young modulus is equal to stress, axial stress over axial strain. Right, so let's plug the values for these ones. Let's force over area. Let's put the force over area for axial stress, and this is the strain. So that is the force over area times strain. Now let's change these ones to the strain, F over area, and the strain would be your dn, right? That's change in length over L. So we will have Young modulus equal to F L, that's L here, over dn A. And if I want to calculate this force is your Qn, by the way. So that is Qn L over dn area. And we want to find this Qn equal to area, these ones, times Young modulus over length L dn. So that's how we get this one. So it's just the stress, strain, Young modulus, three equations, and we rearrange and we can find the force. So that is the force here. The reaction force created is just equal and opposite. So same force and equal and opposite. We do the same thing. We fix this far end here, and we're going to pull these ones. Then if you pull these ones, you will stretch out with df, and you have same equations minus. And then you will do these ones, you will have these ones. Don't worry if you don't get that all this one. And if I superpositions this one, like these ones plus these ones, you will get Qn equal to this minus these ones, all Qn. And Qf, this minus, and this plus. And if I write it into the integration form, in the matrix form, Qn, Qf, Ae over L common, 1 minus 1 minus 1 dn df. Okay, so you can have, this is a stiffness. I think last week we talked about the stiffness. You remember force is equal to stiffness times the displacements. So this is your stiffness matrix. It's called member stiffness matrix. Okay. Don't worry if you don't get all these informations in the great details. Now, in here, let's say you don't need to go through all this nitty-gritty of this one. Let's say this is again the Q equal to KD, the force times displacements. And if I want to, I think we have this ones here. You can look at that one. Now, when you do the displacements, you need to transfer your displacement from global to locals. So if you have a displacement in the global, let's say capital D, you can transfer it into the locals. And there is a cause relationship which is global to locals. And this is a close relationship. I don't want to give you boring stuff, but I can give you that if you have a global, and you have matrix to transfer it into the local. So you can have a relationship between the global and locals. It's like a federal government and state government. Like you should have a relationship between that ones. You have local systems and you have a global system. And there is a relationship between the displacement of the global transformation matrix and you have local system. So that is a relationship because This global system and local system cannot work independently. They need to have a relationship between each other. So that is the D equal to this one. Similarly, force also have a relationship, that global force equal to some cause relationship with the local system. So you have a global force with some relationship with the local. So global force transforms to the local systems. Using these informations, global and locals, that we can plug in. So Q equal to KD, you know these displacements that we just discussed, global displacement, local displacements. If you multiply T both sides, you can cancel this one. So TD equal to small d. This is the force one as well. You remember that this is the force in the global and this is a local force. You multiply T on the both sides, you get this equation again. Now we plug this value. We plug this small d here is equal to TD. We can also multiplication on both sides and you're going to get these big equations, which is the global force. And if you substitute all these metrics, you will get these nice metrics here. And this is the one we're going to use it. If you don't understand any of these ones, don't worry. This is just a simple derivations. We're not going to ask you the derivations, but this is the matrix that we're going to use to calculate the member forces and so on. So if you don't understand any of these ones, don't worry. This is the equations that we're going to use. And when I take an examples, I will going to help you on that one. So we've done these transformations and force vectors. I think the force vectors that we're going to do it, I think later we can do it and analysis procedures. Okay, force vectors I will explain you, and this member force also I will explain you later. So let's do the examples, because if I give you a lot of information, you will going to absorb, not be able to absorb all this information. So let's do the examples first for that calculations, and then I will explain you that force vectors and displacement vectors and so on. So what is that? Determining the forces in each member of the two member trusses, so on, and AE is constant. So we need to find the member forces, we need to find the displacement here, we need to find the reaction forces, we need to find everything here that we done. This is the indeterminate structures. You cannot use the joint methods here that we use on those things. So let me connect you with another device, and we take it from there. You can hear me. You don't need to see me, because these examples that we're going to do it with the writings. Okay. So you can put in the chat if you have any questions, but this is the problems that we're going to solve. Now, step number one that we're going to do it is a modeling, and now we're going to explain you the modelings. So the step number one, modeling. So that is the element number one. That is the element number two. Doesn't matter. You can put one or two anywhere that you like. It's already given in the example, by the way. Then we put the location vectors for that members. So that is the element member, element one, element two, location vector for element one. Now we're going to put the node numbering. So node numbering is 1, node numbering is 2, node numbering 3. Doesn't matter. You can put 1, 2, 3, whatever you like it, but you're not allowed to change after you decided to put those values. And then we will going to find the total degree of freedoms. We are going to find the total degree of freedoms. Total degree of freedoms. Let me find the total degree of freedoms. Now the total degree of freedoms would be 6. That is a 6 total degree of freedoms. Now this is the pin support, and this is pin support. So out of total degree of freedoms, free degree of freedoms, how many? You can say 1 and 2 are free. There are total 2 free degree of freedoms, and there are total 4 free degree of freedoms. If I add them, that become total degree of freedoms equal to 6, because this point, which is pin number 1, it cannot go left or cannot go right. It cannot go right or left. Number 3. So our intention is to start with the free. So 1 and 2 would be free, and 3, 4, 5, and 6 would be fixed. So that is the lowest one. So lowest one that we're going to put is 1 and 2, And then the fixed one we're going to put is 3 and 4 and 5 and 6. That is your fixed one, right? So I hope you understand the modelings. Everything is nice and clear. You can stop me if you don't understand any of these ones. Now, let's say then we're going to do element number 1. The good part about these methods that we're not going to look at the whole problems. We're going to do it, break it down into element by element wise. So let's say element number 1. What is the length of element number 1? Let me get this one here, edit, copy, and then we can paste here. Okay, so that is here. Now in here, element length of the element number 1, I think we can get the length of the element number 1 from this another figure. So here you go. Length of the element number 1 is given on here. So length of the element number 1. Yep. Here you go. So element number 1 is this one, and the length of the element number 1 is 3 meters, which is perfect. Let me draw the element number 1, by the way. So that is the element number 1. It has a location vectors going in these directions. It has a number 2 node. Number 2 node. It has a number 3 node. It has degree of freedom 1 and 2. Degree of freedom 1 and 2, and it has degree of freedom 3 and 4. And the length of this element is 3 meters. Right? So I just copy these whole things. What I done? I just copy this part in here, nothing new. Right? That is element number 1. I collected all the informations. I just copy these ones. I did not put the load. I just copy that element number 1. Let me ask you any questions. So far, so good. Any questions? Anything? Or is it too fast? Things. Okay. Once you done these ones, then we will going to go and get that stiffness matrix. We're going to go and get this very nice and beautiful stiffness matrix that we have developed in the theory. Here you go. Here you go. So that's your stiffness matrix. Copy. And there you go, stiffness matrix here. All right, now here. Now in here, we're going to have this is, let's say, stiffness matrix represented by small k1. And if you look at this one, this is a global global coordinate. You can look at this x and y. You can look at in here. That is the global coordinate. So global coordinate, which I have a 0, 0 here. So I can write it here. So that would be 0, 0 here. And this point would be x is 3, 0. And this would be 3, 3, 4. Right? So you can have 0, 0 here across 3 meters and y is 0. Across 3 meters and y is 4. So that is the coordinate systems which I have written. So if I want to write the coordinate here, that it will be 0, 0. And that would be your 3, 0. That is the coordinates respect to the global coordinate. It's given already global coordinate systems as you can see here. So before we do the K1, we need to calculate a lambda x. Now the equation for lambda x would be x of far node minus x of near node over length. How do we know which one is the far node and near node? This location vector is telling me that is a near node and this one is far nodes, right? So I can say that this is the x near node coordinate, y near node coordinate. I can say that this one is the x far coordinate. This is y far coordinates, right? So this is these arrows telling me which one is near node, which one is far node, and that is x far, y far, x far, y far, right? So now we can plug the value. X far is 3. X near is 0. Over length is 3 meters. So lambda x is equal to 1. Lambda y coordinate of far node, y coordinate of near node over length L. So y coordinate of the far node is 0. Y coordinate of the near node is 0 over length 3, which is 0. So lambda x and lambda y calculated. Now let's do the K1. K1 is equal to AE over L. I'm just copying it from here. Lambda x square. So lambda x square is 1 square is 1. Lambda x times lambda y. So 1 times 0, which is 0. Minus, we put minus lambda x square 1. So this minus does not mean that you need to square it. It's not like minus 1 square. No, it is minus first and then it is square. Okay, so you don't need to do these ones. It is different than these ones. Okay, in case when we get the minus, you will understand that. So we put minus and then 1 square is 1. Then minus 1 times 0 like this. So it's 0. Now we can have a lambda x times lambda y, which is lambda y is 0. So therefore 0. Lambda y square. So that is 0. This is minus. So that is 0 because we have lambda y. When you see lambda y, they are all 0. Lambda x square minus 1. This one 0 because lambda y is 0. This one is 1. This one 0 because lambda y. This one 0. This one 0. Lambda y is 0. This one 0. This one 0. When you see the lambda y, that is 0. Okay. I don't want to rush it. If you don't understand any of these ones, you let me know. Or anything that does not understand or where these numbers coming from or which xn or which fy and so on. Now in here, the good part about this one is a symmetric. As I said, all my lectures, I don't want you to blindly follow. I always give you the stop signs to recheck. What does it mean recheck? Look at these ones. This is completely symmetric matrix. What is symmetric matrix meaning? You look at these 3 guys and look at those 3 guys, same. So whatever the numbers you're gonna get here on 3, the row, they will be same. So look at these ones. These numbers, these numbers, these numbers, these numbers, these numbers, and this number same. Oh, it looks same. Perfect. Perfect. It's give me the validation that I am on the right track. So that's the beauty of symmetry, beauty of our trust methods. Very nicely seated. Then you have, look at the another one. That this guy and this guy is same. So look at these ones. Look at these two and look at these two. Same. Perfect. This guy here and this guy same. Look at this. These guys and this guy same. Perfect, right? It's same. Someone said that if I calculate this one, can I copy here? Well, if you are confident, you can do that. But I don't recommend to do this one, so you don't have verifications. Another verifications. This block same. Look at that. Very nice. Very nicely seated. Another one. This block same. Look at that. Wow, that is perfect. So you have second verification. Another verification, all these numbers on the diagonal always positive, by the way, because they are all square. You can see that. There is a third verifications. You cannot go wrong. Some students tell me, yeah, still you can go wrong. Yeah, of course you can still go wrong, but it is not that I'm just putting you in the dark room and you have no help. I'm giving you the torch that will help you to find the way around in the dark room. So this torch is saying that this is the information that you can have verifications. Now, what is this one? Near node of x. So you can come back here. Near node of x 1, 2. So you can put the degree of freedoms 1, 2, and far node of x and far node of y. So far node of x 3 and 4. So you can put 3 and 4. 1, 2, 3 and 4. The length we got is 3 meters. So you can change these ones to 3. So K1 is equal to AE 1 over 3.33. 0 minus 0.33. 0, 0, 0, 0, 0. I'm just dividing by these 3 all the way. 0.33 minus 0, 0.33, 0, 0, 0, 0, 0. And your 1, 2, 3, and 4. I will give you the Excels. You will gonna like the Excel one. So that is the element number 1. Now we're going to do element number 2 now. Same procedure, by the way. Element number 2. Let me get that figures. Let me copy this one first because we're going to need it, these ones. And paste. So that's this one's here. Now element number 2. We're going to copy this. Where is it? There you go. This is element number 2. That is the element number 2. All right. So that is the element number 2. What is the length of element number 2? We can calculate that. So over here, we have this triangle, which is 3 meters and 4 meters. So if I want to find that 3 square plus 4 square, which is 9 plus 16, which is square root 25. So length would be 5 meters here. Let me draw it up. This is the element number 2. Location vector is here. Degree of freedoms is, I'm just basically copy these ones. 1 and 2 and 5 and 6. So 5 and 6. Just copy. Okay, I'm not doing anything new. That is number 2 and that is number 1. So number 2, that is number 1. The length is 5 meters. And this one is near node, by the way. This one is far node because this location vector is giving me the hint. And what else? So the coordinates, so that would be 0, 0 here because this is your x 0, 0 reference. When you come back here, you need to go across by 3 meters. You need to go up by 4 meters. So 3, 4. So that is 3, 4. Right. So you know these equations, right? These ones. Let me go back and get that equations for you. And then we can put it here. Can put it here. Control V. Now, in these equations, let's try again. Here we're going to write the small k2 is equal to AE on L. Small k2, K stands for stiffness and number 2 stands for element number 2. Let's put it here. Oh, we can calculate the lambda x first. Let me cancel this. We can calculate lambda x equal to x of far node minus x of near node over length. Now this is 0, 0 here, and that is x of near, y of near because that is near node, and that is x of far and y for far. So x of far is a 3. X of near is a 0. Length is 5. So 3 over 5 equal to 0.6. X of y, lambda y far minus y near over length. So y far is 4, near is 0. 4 minus 0 over 5. 4 over 5 equal to 0.8 using the calculators. Now we can use the same equations here and plug the value. So K2 is equal to AE on L lambda x square. Lambda x square 0.6 square 0.36. Lambda x times lambda y, 0.6 times 0.48, 0.48. By the way, this is 0.6 times 0.48, 0.6 square. This one minus 0.6 square. By the way, this minus does not mean that you need to put minus in your calculator 0.6. No, minus outside and then 0.6 square. So minus 0.36. This one's minus 0.6 times 0.8, which is minus 0.48. And this one's, which is minus, lambda x times lambda y, 0.48. Lambda y square, which is 0.36. Oh, lambda y square 0.64, sorry. Minus 0.48. Minus 0.64. Lambda x square minus 0.36. Minus 0.48. 0.36 positive. 0.48. Minus 0.48. Minus 0.64. 0.48. And lambda y 0.64. Now, we can do the verifications. As you know, the styles, stop signs. These guys here, same as this one. These guys here, same as this one. This number, same. Bang. Same. Look same, right? Perfect. Okay, another one. This block same. This block same, right? Let me use another color. Block and this block same. Look at that, numbers are matching. Perfect. Diagonals all positive. Perfect. Matching. Then we put this near node of x. Near node of x is 0. Near node of x is 1 and 2. Degree of freedoms 1 and 2. Far node of x, far node of y. Number 5 and 6. So that is number 5 and 6, 1, 2, 5 and 6. And length is now 5 meters. So here we have 5. So AE 0.36 over 5. Let me use my calculators here. So the calculators I'm going to get is in the Excel. So 0.36 over 5. 0.072. 0.48 divided by 5 is give you 96 minus 0.072, 0.48, 0.096. I'm just dividing by 5 all. Divide by 5. 0.48, 0.096. 64.64 divided by 5. 0.128. 48 is 0.096. 64 minus 0.128. 36 minus 0.072. 48 is minus 0.096. 36 0.072. 48 0.096. That would be minus, I believe. That would be minus. Then you have 0.096 minus 0.128. 48. That would be 0.096 and 0.128. Right, and then you have 1, 2, 5, 6, 1, 2, 5, 6. Right? Unmute yourself if any number does not make sense. Once, then we can assemble the matrix. We can assemble the matrix. How do we assemble? Capital K equal to small k1 plus k2. So capital K equal to A. How many total degree of freedoms? You have total 6 degree of freedoms. 1, 2, 3, 4, 5, and 6. And here you have 1, 2, 3, 4, 5, and 6. Okay. So 6 by 6. Why we are write 6 by 6? Because you have 6 total degree of freedoms. Look at here. You have total 6 degree of freedoms here. If you have 8, then you need to write 8 by 8. If you have 12, you need to write 12 by 12. If you have 4, you need to write 4 by 4, and so on. So that is the total degree of freedoms. Now here, this is columns 1, row 1. So let's go back and check. Column 1 and row 1 is 0.072. And column 1 and row is 0.33. So 0.33 plus 0.072 gives me 0.33 plus 0.072. It gives me 0.402. I hope it is making sense. Now, column 2, row 1. So column 2, row 1, 0.096 and 0. So 0.096. Column 3, row 1. There is no, so that there is no here, so that is 0. Column 3, row 1, minus 0.33. So you have minus 0.033. Number 4. There is no number 4 here, so should be okay. 0. Number 4 and 1 is 0. Number 4 and 1 is 0. Number 5. Column 5, row 1, minus 0.072, and there is nothing here, so minus 0.072. Column 6 and row 1. Column 6 and row 1, minus 0.0, so column 6 and row 1, minus 0.096, and there is no column 6, row 1, so minus 0.096. I hope you understand the drill now. Number row 2, columns 1. So row 2, columns 1, 0.096 and 0. So that is 0.096. Column 2, row 2. So column 2, row 2. There you go, 0.128. And there are 0 here. So 0.128. Column 3, row 2. There is no here. And this one 0. 0, 3, and 4. 5 and 6, row 2. Row 2, 5 and 6, these are here, minus 0.96, and you have minus 0.128. 3, 1 and 2 here, minus 0.33, and there is no 3, so we can copy these ones, minus 0.33 and 0. Minus 0.33. If there is no any numbers there, you can just ignore it. So I just copy these ones. Number 3. I hope it is makes sense to you. Just you need to find the numbers that make sense. 0.72 minus 0.096, 0, 0, 0.072, 0.096, minus 0.096, minus 0.128, 0, 0, 0.96, and 0.128. Right. So I hope you understand these ones, where all these 6 by 6 matrix coming from. It's just adding K1 and K2. If you have next things that we're going to develop is a force vector. How are we going to develop the force vectors? I'm going to show you. Now to develop the force vectors, we can just copy these ones and we're going to paste it here. Paste it here. Okay, so to develop the force vectors, you can have, you remember that I think we done this degree of freedoms free and fixed. So here you go, free degree of freedoms and fixed degree of freedoms. You remember that, right? Free is 2 and fixed is this one. So force vectors generally like this is represented by capital Q and it has only 1 columns and totals degree of freedoms that you're going to put 5 and 6. So that is your force methods. Now, when you do the force methods, you need to divide them into 2 things. So that is your free degree of freedoms and that is your fixed degree of freedoms, right? So you remember that, right? At the start, we done this free and fixed. So you can have free and fixed. So you can see. So if you have 3, 3, you need to draw the line at 3, 3. If it is 4, 4, you need to draw the line at 4, 4. So you can have free and fixed. Now, you can go back in the figures. There is a 1, there is a 0 force. So there is no any force in the 1. At 2, there is a force 2, but it's going opposite to 2 because 2 is positive in this direction, but 2 is going down. So you can put -2, right? Kilonewtons. You can see that, right? That is the force vector. That's how the global coordinate systems would be useful. Global coordinate systems, right? So these global coordinate systems used to get the force vectors, right? You can see 1 and 2. There is no force in the 1. There is no force in the 2. When you look at the fixed degree of freedoms, you have Q3, Q4. So Q3, Q4, Q5, Q6, which is your reaction forces, right? There is a reaction force here, which is unknown. This is a reaction force unknown. So basically in here, in the Q vectors, there are a few things. In the Q vectors, free degree of freedoms, free degree of freedom represents the external force. It can have value of 0 to any value that you needed. Q vectors, again, when you have a fixed degree of freedoms represents unknown reaction forces. It could be any value like Q2, Q3, Q4, or something like that, depending on what is this one. So I hope it makes sense. This one, 2 notes that your free degree of freedoms in the Q vectors represent the external forces, like external forces that you have. And these are basically known. So this is basically known values. And these are basically unknown values. And that's also fixed degree of freedoms that's the vector represents. Now, another one is called displacement vectors. So the displacement vector D that we're going to put again 1, 2, 3, 4, 5 total degree of freedoms. Again, divide them into 2. And this is opposite. You can see this D1 and D2 are unknown because we don't know what is the displacement here at this particular point. What is the displacement here and what is the displacement here? We don't know. D3 and D4 0 because this is fixed degree of freedom. They are 0 because there is no any displacements because fixed supports, and 5 and 6 are 0 because they are fixed supports. So I can also write here that displacement vector with this is your free and this is your fixed. With free degree of freedom represents unknown displacement, right? And vector with fixed degree of freedoms represents known degree of freedoms, known displacements, and which is generally 0 unless you have settlement, generally 0, right? So that's all good. So now you have force is equal to stiffness times the displacement, and we're going to plug the values. So here you have Q is 0 minus 2 and Q3, Q4, Q5 and Q6 is equal to K. I think you remember that big K that we're going to copy. AE, and we will have 0.405, 0.096 minus 0.333, 0 minus 0.072 and minus 0.096, 0.096, 0.128. I'm just copying it from there on the top, okay? 0.096 minus 0, and you know where this all coming from. 0.33, 0, 0.330, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, minus 0.072, 0.096, minus 0.096, 0, 0, 0.072, 0.096, 0.096, 128, 0, 0, 0.096 and 0.128. I just copied that numbers, okay? There is nothing new, I put it. I'm just putting that assembly. 1, 2, 3, 4, 4, 5, 6. Sorry, this is kind of a boring for you to see, but yeah, I can't make it that more than this entertainment, but I'm just plugging that value. D1, D2, 3, 4, 5 and 6 are 0. Now you can do the partitions. Like draw the line across from 2. Right? You can see that 2 is coming from this free and fixed. So this is your free and this is your fixed. And again, you can draw the line from 2 because that is the 2. If you want, you don't need these numbers. From the start itself, you don't need these numbers. We're not going to use it. I will show it to you. So if you want, you can put the dash to save some time. So you can just need to obtain these numbers only. So from here, we can type 0 minus 2. And that's I grab it here and AE. And we can have this value 0.405. We can have 0.096 and 0.096 and 0.128. D1 and D2, right, is coming from here. So our question is to find D1 and D2. I think you know this one, right? A equal to Bx. You can see this is the unknown X value that you can have this matrix. So if I do B inverse times A equal to B inverse B equal to X, and that become your 1, or it becomes nothing, right? You can cancel those ones. So we need to find B inverse. Your B equal to 0.405. I just ignored this AE at the moment because it's constant, so no need to worry. And 0.128. So for that, we need to find the determinant B. I hope you know this matrix, which is to calculate the determinant B. We multiply these diagonals. We multiply those diagonals, and let me put that 0.5 times minus. So you have 0.043. That is the determinant. And to find the B inverse, we have 1, that B, and we swap these numbers. And then we put the minus in front of it. We don't need to swap it. We just put the minus in front of it. So 1 over that 0.128, 0.096 minus 0.405. So we divide these numbers by this. So 0.128 divided by 0.043, you get these numbers by these numbers, by the way, 2.98. These numbers 0.096 divided by 0.043, you get 2.23 minus 2.23, and these numbers divided by 0.043, 9.42. Right, so now we have these equations. B inverse, which is 2.98 minus 2.23 minus 2.23, 9.42, and the X A value 0 and minus 2, and minus 2 equal to D1 and D2. By the way, this is 1 over A because you need to invert, you throw it on the other sides, right? So we can, the multiplication of matrix 2.98 times by 0 plus minus 2.23, this row times by columns, and minus 2.23 times by this 0 plus this 9.42 times by minus 2 is equal to D1 and D2. Sorry, this is boring for you, but this is, I just want to highlight that this minus 2.23 times by 2 positive, so 4.46, and that would be 9.42 times by 2, which gives me 18.84 is equal to D1 and D2. So if we know the area, so D1 equal to 4.46 over AE. If we know the area and Young modulus, we can put it there. D2 equal to 18.84 over area. What does it mean? That means that these values, what does it mean? That these, let me get these ones, Control C. And what does it mean for you? That its values, these displacements in D1, so this point can go in these directions by 4.46 over AE. And these points, I think that would be minus, right? Yep, that is minus. Yep, that is minus. So that is minus here because I can see that this point can go down. So this point can have a minus 18.84 AE. Right, so that is the displacements. So we found the displacements at these nodes, unknown displacements, all the unknown displacements. Now we can find the reaction forces. So we can grab these ones. Q3, Q4, Q5, Q6 is equal to these guys we're going to get with AE. So AE, and that guys is minus 0.3330, 00 minus 0.072 minus 0.096 minus 0.096 minus 0.128, and then we also multiply this by this D1 and D2. So this D1 and D2. Now we can substitute the values Q3, Q4, Q5, and Q6 is equal to AE. This value was minus 0.333000 minus 0.072 minus 0.096. D6 minus 0.128. And D1 and D2, we're going to substitute that one. This is minus, by the way, 4.46 and 18.84. 4.46 minus 18.84, right? Okay, so then here we can cancel this and this. So Q3 equal to these numbers times by these numbers plus 0. By the way, these ones times by these ones times by minus 18.84. So if I substitute that one, 3.33 times 4.46, you get 14.85, and that is minus. Q4, that is just 0. Q5, these numbers, minus 0.072 times by 4.46 plus minus 0.096 times by minus 18.84, and that is kilonewtons. So minus 0.072 times 4.46 plus 0.096 times 18.84, you get 1.49 kilonewtons positive. And last one, Q6 is equal to minus 0.096 times by 4.46 plus minus 0.128 times by minus 18.84. I hope it is making sense. It's nothing I can make more entertainments, just recording these examples for you in case you want to do it again. But I hope it is making sense what we are doing, 1.98 kilonewtons. So I can show you what is those Q3, Q4, Q5 meaning. That meaning that Q3 minus 18.45. So Q3, the reaction force is going opposite to 3. The minus does not mean that is the wrong answers. Minus meaning that is opposite to this one. So you have a 14.85 kilonewton reaction force here. 14.85 kilonewton reaction force here. Q5, you can have a Q4 0. So there is no force here, 0. And this one's Q5 going this way, and that is 1.49. And Q6 is going up 1.98 kilonewton. So that is just a reaction force. I think there is something wrong here. I think that's should be matched 14 point. I think this is 14. Just check my calculations, but the procedures are same. This is 1.98, 2 going up, 2 going down. That's all good. This is should be 14.9 and this 14.9 going this way. So I hope it is making sense. Now, before I go to these ones, I need to show you with the Excels as well. Copy, and when I do it in the Excels, it will going to make more sense what we done it in the manual. I think the manual one is not going to appear here. Is it gonna appear? We will check later if it is going to download it or not. Yep, it is coming back to here. Okay, well done. All right, so it is coming. And these equations we needed. So let's say we want to solve these ones. Let's say I want to put elements. So element 1, element 2. There are 2 elements. If you have more than 2 elements, you can put the more than 2 elements. Okay, but this is 2 elements. I hope you can see the screens. Let's put it in the middles. Now there are 2 elements, so that's all good. Now let's say you want to have a what can I do? Let's say length. Let's say length we want in the meter. So the element 1 has a length 3 meters. 3 meters, and element 2, you remember that we calculated 5 meters. You remember that, right? I can show it to you the things that if you don't remember that somewhere we done the calculation for element number 2. It's not appearing, but still. Yeah, no, it's not. It's still synchronizing online. So you remember that 3 square plus 4 square, we done the 25, so that was a 5. Now, we can do the coordinates as well. So we can do the coordinates. So let's say, now we can do lambda x straight away. Lambda x. You remember for element number 1, the lambda x was 1 and 0. So lambda x was 1 and lambda y was 0, right? Now you remember for these ones, I think it's not coming it up. It's not coming it up. So you remember that lambda y was, how much was that? Let me check on my this one. So that was okay, because I think this are not going to synchronize. Let me synchronize. Okay, so lambda x, if I remember that one, so in our case, lambda x was 0.6. Lambda x was 0.6 and that was 0.8, right? If you remember that. Now area, we can put area, dummy area, let's say millimeter square. Later on we can use it. Let's say use 10,000 for both. And the Young modulus, we can put Young modulus Newton per millimeter square, which is 200. Let's say steel, so 200. 1, 2, 3, and let's say 200. All right. Anything else? I think that's it. We don't need anything else. So let's say we want to have an element number 1. Let's use different colors. Let's say we want to have element number 1. And element number 1, you remember that was a K1. You remember that K1 we done here, K1. So in the K1, I will keep it this one in front of us. In K1, we have these. Let's say let's do this x, lambda x and lambda y and so on. So in K1, if you remember, equal to lambda x. This is lambda x square. 8. Enter. Equal to this lambda x times lambda y. Lambda x times lambda y. Bang, done. Minus lambda x square equal to minus sign and then bracket. Don't make mistakes here. And then square. Okay, don't make the minus sign and then, because if you do these ones, look at this, without the brackets, it will give you the one answer. That is wrong. You need to have this bracket done and then after lambda x square. I think still it is not giving me the right answers, but you can do this square like this and then it give you minus answers. You can see that. We can do 4 by 4 and just the border and doing this way. Minus lambda x minus lambda y minus equal to lambda x lambda y. Right, equal to these ones. Lambda x times lambda y. I hope you know what I'm doing. Lambda y square equal to lambda y square. So that's all good. Minus lambda x times lambda y equal to minus bracket lambda y. Don't make mistakes here. You need to do these ones, okay? Otherwise, it will give you the positive answers. Okay, minus lambda x square and then square and bracket over. And equal to minus lambda x minus lambda y. This one times this ones. Lambda x square, and lambda x times lambda y. So it will make sense to you now how you do the hand calculations, right? Minus lambda x times lambda y equal to minus lambda y square. By the way, I'm looking at here, lambda y square. And then you have lambda x times lambda y. Lambda x times lambda y. And then you have lambda y square, lambda y square. So if you compare with our calculations, you can see 1 minus 1 0 0 0 0 minus 1 0 1 0. That is perfectly matched, right? I can copy these ones for you and see if it is matching or not. Copy, and let's put it here, small one. So you can see 1 0 minus 1. And the beauty for this one, see if I come back here and let's say my change mine 0.5, I put it here, boom, bang, it is changing. 0.6, look, changing. Wow. So you can see that, right? It's interactive. If your friend comes and says my lambda x is 0.65 and I have this 1.8, it's give you the answer. Bang, look at that. So yeah, it is a very useful tools and you can use. Of course, unfortunately, you don't have this one in your exams. Otherwise, you're gonna crack it very well. But I hope this makes sense. And you have near node. I think if you look at this ones, element number 1, 2, 3, 4. So you can have 1, 2, near node, far node is 3 and 4. So that is the near node. That is the near node X, near node Y, far node X, far node Y. I hope it makes sense. And the arrow will going to tell me which one is near node and which one is far node. So that's here and that's it. Now, we need to divide by length. You remember that you have a length as well. So we can Control C. Let's do it here. Control V. Control Z. So we don't need to do Control C and Control V. Let's say we have this K1 and equal to these ones, divide by length. But we want to log these ones, right? Press F4 in your keyboard, or you can put $sign in front of it. So look at these ones, bang. If I move it here, these numbers changing, but this one is locked, it's not changing. Bang. 4, this is all good, and you can have selected all and scroll 1, 2, 3, 4. Bang. You can see that, nice and beautiful. Okay, I like it. These ones 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay, perfect. Now we need the global stiffness matrix in the form as well. So you can see if I change the number here, bang, everything is changing. If I put number here, bang, it's changing, right? Let's put 1 and 0, that's we needed, right? So it's very nicely flow what you needed. So let's put this 4x4 matrix. Then we need to have a global matrix. Okay, we can't copy these ones because sometimes it does not work. So K1, and we just here, and 1, 2, 3, 4, and 1, 2, 3, 4, right? So you just copy it in that format. And here you have 1, 2, 3, 4. Now 5 and 6, 0, 0, right? Because there is no any row and columns for 5 and 6, so we can put those are zeros. So we can match it with that ones. So 5 and 6, and then you have 0, 0, 0, 0, 0, 0, and 5 and 6 are 0. So I hope you understand. If any numbers, any rows not required, you can put 0, 0, 0 because we need the 6x6 matrix. 5 and 6, right? Because we have total 6x6, 6x6. So K1 done. And you can see that if I change these ones, 0.5, bang, all are changing. If I say 0.6, all are changing. Well done. Same story, nothing so much. We're going to do element number 2. So element number 2, and K2. So yeah, so same formula. in here, we going to, okay, we just copy these ones. Let's say copy these ones, Control C, Control V. And when I see these ones, we just move it to 0.6. When I see these ones, we're going to move these ones, we're going to move these ones. You are more than welcome to do it manually because we have these equations. 0.6 here and 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 just, I hope it is not overwhelming for you, just changing the lambda x and lambda y for element number 2. So that's here and that's R here and these are here. Okay, so now near node, far nodes 1, 2, 5, 6. So 1, 2, 5, 6 and 1, 2, 5, 6, right? Similar story, we can have a K2 and length divide. So we can copy these ones and we copy these ones. Okay, now we can divide this number by length of these ones, F4, lock it or $ in both of them, and we can just scroll it here and scroll it down. So that is the length, and you can do the area and Young modulus division as well. Here you can do and log them. Okay, so you can have area divided by this one. Now K2, here K2, and from there K2, we can put 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. Right, now 1, 1. So here 1, 1. And 1 and 2 here. 3 and 4 is not there, so we can put 0, 0. And you can scroll it down up to here. And 3 and 4 is 0, 0. So you can have 3 and 4, 0, 0. And 3 and 4. There is no 3 and 4. So those are 0, 0. Now, these ones here equal to these ones. These ones equal to here, these ones. Equal to these ones here. So we can just do this and do this. You have equal to here. I'm just putting the respective columns, okay? Therefore, this computer likes these methods because it has very definite columns and rows that numbers where it's gonna go, it will gonna tell you. So there you go. And these ones here. Now capital K is equal to K1 plus K2. Look at these ones. Sorry, I think a little bit faster, but I think you know what I'm doing, so you can do it yourself as well. So here you go, K1 plus K2, and bang, go across, go down, bang. And the beauty of these ones is fully interactive, like this. And it's fully interactive, meaning if someone say that, hey, change these numbers to 0.5, then changing, change 0.4, changing. It says change this one to 0.2. All are changing K1, K2, and K3. So all are working very nicely, and I hope it is helpful. So we have 0.6 and 0.8. So, and it's matching. These numbers would be matching with your hand calculation. That's you can do it by yourself. The calculation of member force, like here you go. You can calculate the member force using the equations. That one's the equation is very simple. This equation. So you can have area, Young modulus, lambda x is there, lambda y, you know, you have a displacement, so you can just need to multiply these ones here. The procedure is given here, so you can go through it by yourself. That would